Good day everyone, and welcome to this presentation where we're going to introduce you to Multotec's pulping chute and how its application in the diamond beneficiation process and tailings plants can be of benefit to you as a plant. We're going to be harnessing the forces of nature and effectively showing you the physics that allows us to create the simplistic solution to replacing the secondary scrubber. And that's effectively what it is. It's a replacement for the secondary scrubber. I've got a little video that we'll show you just shortly. And that'll give you a far better idea of what we're talking about, and it'll bring a few questions, and hopefully we'll have quite a few of those answers in the following slides. But before we start with that, the reasoning behind looking at a replacement of the secondary scrubber is because of the high costs. The operating costs due to excessive power consumption, the wear and tear, which is the mechanics, having to replace the liners as well, and the liner degradation, is part of the reason why it is such a costly exercise to have a secondary scrubber. And effectively, its efficiency is also causing a few problems for a number of people. And if you think about what it's meant to be doing, the deagglomeration that is required due to the high percentage of clay and fines in the ore feed, which are formed or forming clay balls and therefore entrapping the diamonds. And this is what we actually are supposed to be opening up and washing it out. And the secondary scrubbers is not doing the job quite as well as it should be. Please take a look at the video, and then we'll go through the rest of the theory and what it's all about. Great, sorry about that. The pulping chute and its feed characteristics, let's start with that, because effectively we're going to have to get quite a bit of information from you as the end user to be able to understand what we're designing and how we're going to design it and why. So there's a number of bits of information that are quite crucial to start this process. Bearing in mind, again, as I said, we're looking at the secondary mineral processing circuit only. We want to understand what your dry tonnage is, what is the feed tonnage required. We want to understand also what the water availability is, because it's a crucial element that we have a minimum of 1-to-1 ratio of ore to water feed. This is pretty much non-negotiable. You either have to, you can have more, but you cannot have less. So that ore to water ratio is quite critical. So we will then ask you what your density is of your ore body, and we'll want to understand what the percentage of a clay is that you're experiencing. These are quite important factors. We're moving further into more considerations. We'd like to actually understand exactly the space that the current secondary scrubber is taking. It doesn't have to be exactly there, but effectively that's normally where people try to look at placing it. We want to understand the feed chute arrangement to the scrubber, and that way we'll able to understand how to maintain the modifications to the feeding of the pulping chute. There's another critical factor, and that the angle of the pulping chute has to be at a minimum, at least. It can't be any shallower than 21 degrees. It can be steeper, but it definitely cannot be shallower. We found that that's the only way we get what you'll find just now when we talk about the potential energy of the gravitational forces. We need that. That's quite important. The chute length will then be determined, and the number of wave generators that we'll be requiring due to the length of the chute will be factored and calculated based on that. What we are trying to do is make sure we generate sufficient energy to lift the material to the top of the wave generator and force it back into the flow direction of the material behind it. So all of these factors are quite crucial to us designing correctly. There's a few more process parameters to consider: drive motor size, current scrubber feed capacity, your particle size distribution, and specific gravity. Water consumption, as I mentioned, is very crucial, and the bulk density of your feed. Also, there'll be a couple of questions we have to ask around installation and test parameters. And for your own benefit, you can look at putting and should put in electronic devices that will allow you to control automatically or manually both the feed and the ore being fed into the pulping chute, and this allows you a certain level of control. Just a basic design of what we would normally used for feed to the pulping chute. It's a manifold type of system. And here we're looking at the ore and feed being controlled, both with valves on each one of those pipes. And that'll allow you to have a certain level of control. Obviously, there's a safety factor to that. When you need to switch it off, then that's what you need to have in place. Let's start looking at some theory. So effectively what we're talking about is utilizing natural energy, potential energy. And we'll go into a little bit of theory of the potential energy, but you're wanting to take the potential energy and transfer it into kinetic energy and allow then the velocity of the water and the flow of the material to then kick in and actually create that washing action. We can look at a variety of the components on how it actually works, and you'll see it in one or two slides coming down. But remember again, we're wanting to separate the diamond from the clay ball, and that's why we're creating a washing action. Effectively, this is a giant washing machine. So there's a number of ways this actually works. You have to elevate the material to the top of the pulping chute. You've got to get a certain amount of height, and then you've got to release both ore and water at the same time into the chute. It's going to create this washing action where it's flowing straight down towards the first wave generator. It then throws the material back onto itself, back into the stream of flow, but at the same time at an angle, so that it pushes out towards the sides of the chute. It does exactly the same wave action again, throwing it back onto itself, and then feeds the material straight back into the center once again. And this continues with the number of wave generators that you've got into place. Sometimes we only have 2 sets, other times we have 3 sets. Extreme cases you can start looking at more, but generally we run up to about 3 sets of wave generators in most pulping chutes. Now let's talk about the potential energy, which is part of the physics. Here I'm just keeping it simple. It's just standard P for at this case. You could use U and G because we're talking about gravitational forces here. So it's potential energy, gravitational. Now there's the formula right there, but what are we actually trying to do? The objective is to convert the potential energy to kinetic energy in the most efficient way. And how we do this is lift it up to a height, get some elevation, and then throw it through the pulping chute in conjunction with both ore and water at the same time. This creates acceleration. So the acceleration is increasing the velocity, and the velocity is obviously immediately assisting improve the kinetic energy. And that's quite important because that's effectively how it works. Look at a wave. This wave action is what you have seen if you've gone to the beach, and this is exactly the process that we're encouraging and manipulating in a pulping chute. Basic design. We don't use this design very much anymore, especially because the retarder bars at the end are decided that just don't give quite the efficiency that we want, but this is a standard arrangement. Again, looking at the wave action, we are moving the material back onto itself into the direction of flow, and that allows the deagglomeration. It allows that washing effect. A simple side view of it, making sure that we're maximizing the utilization of that available energy. It is a critical factor for the washing action because you're wanting to create turbulence. You're wanting to improve that washing efficiency. And this theory of reverse flow, depositing the material backwards, is really enhancing this cleaning action. The chute is rather adaptable. You can add covers if you want, splash guards if you want to call them those. We can take it at some time and round certain corners just to improve the material hang up so that the material is not going to stay there. You're wanting to release as much material as possible. And occasionally you might need to just sharpen, shave off a few corners here and there. So that's often something to look at. The ore flow, for example, can be controlled, and this is where it gets quite critical on the discharge side, because what we'll be doing is feeding the discharge backwards onto the screen. It allows far greater efficiency across the screen cloth. You improve your screen drainage, you reduce your impact to that screen cloth, and this is all part of an efficient washing process. This is what it looks like. So this backward feeding discharge chute flows directly onto the very back end of the screen cloth and immediately improves your efficiency. As we mentioned, less impact on the screen, full utilization of the screen area, longer life on your screen cloth. You can even look at removing one row of blank panels to increase your area for screening. And by feeding it backwards, there's a possibility to add an additional row of spray bars. So these are the kinds of alternatives and adaptations to your pulping chute that you can start looking forward to. Let's look at safety. Now we're talking about return on investment for the next 3 slides. Return on investment is part of the reason why this is such a good option to think about. You have no moving parts. Your environmental compliance system is immediately improved because of no oil spillage. There's noise reduction. There's reduction of both your rigging and or maintenance. Thinking about downtimes, for example. Every time you have a downtime, you've got a huge factor when it comes to safety, people hurting themselves. Reducing your spillage, you're reducing, again, your inspections and your downtime on that last point. Let's look at some energy savings. And this is where it really kicks in for a lot of people. There is no power consumption. And if you compare that, I've put a little bit of information. The installed power of 8 times 8,000 is your annual cost of power consumption per scrubber. Now, I just said no power consumption. That's a massive saving. And the last part of your return on your investment factors is effectively looking at your capex and operating expenditures and immediately look at your reduced downtime. Reduced downtime is one of the biggest problems for most mines because of the cost of loss of production, the cost of having to have labor on site. You've got a number of factors of like stock holding that you don't have to worry about. You don't have to worry about lubrication systems anymore. You don't have to worry about your maintenance, replacement items. But here's one of the big points, and that is your improved diamond recovery. And I think that's a very big point. So thank you very much for taking the time to listen to me. I hope it was informative, and I look forward to the questions and answers.